Hey there guys, Mr. Carlson here. Let's talk about equilibrium. If we were to take a look at this chemical reaction right here, we'll notice that we have this double arrow, this double half arrows I guess we could call them right here, and that's to indicate that you have a reversible reaction. Technically all chemical equations or chemical reactions are reversible, which means that we can have the forward reaction happening where we've got these N2 molecules reacting to form N2O4, but then we can have the reverse reaction happening at the same time, where the N2O4 is breaking down back into the two NO2s. A lot of the chemical equations that we've dealt with have this right here, just an arrow straight across, saying that we're going from reactants over to products. And we use that for chemical equations where that essentially happens, where most of the reactants are getting converted into products. We call those product-favored reactions. But not all chemical reactions are like that. We get some where maybe only some of the reactants get converted to products. And still even some other reactions where hardly any of the reactants get converted to products. For those ones we would call those reactions reactant-favored. But if we take a look at this graph right here, we can see what we mean by equilibrium. So all chemical reactions will reach a point at which we call equilibrium, where essentially the reaction stops. If we look, we can see at the beginning, so at time equals 0, at the beginning of the reaction before anything has started to happen, we've got a lot of reactants and no products. But then as the reaction starts to proceed, our reactants are going to decrease in concentration because they're being used up, and then our products are going to increase in concentration because they're being formed. At a certain point, what's going to happen is we're going to reach a spot where the products and the reactants are going to essentially stay constant for their concentration. They're not going to change anymore. And at that point, that's when we've reached equilibrium. So right there, that's where this equation or this chemical reaction has reached equilibrium. It's when the products and the reactants stay at a constant concentration. They're not changing anymore. A key thing to note about this is that sometimes students think equilibrium means that you're reaching a spot where everything is equal, where you've got an equal amount of everything. And that's not at all what it means. It just means you've reached a point where the forward reaction and the reverse reaction are happening at an equal rate. So for this, for example, the NO2s combining to make N2O4 is happening at the same rate that N2O4 is breaking back down into NO2s again. So the forward and the reverse reaction happening at the same rate, that's when this happens right here, where your concentrations are now not changing overall. It's at equilibrium. So that's what we mean by equilibrium. Again, some chemical reactions, equilibrium lies far to the right, meaning most of your reactants get converted to products, and then other chemical reactions lie far to the left, meaning hardly any of these get converted to products. And then there's everywhere in between as well. Part of equilibrium is calculating this equilibrium constant K for reactions. Our equilibrium constant is essentially calculated by taking the products divided by the reactants. And it's essentially telling you, your K value is essentially going to tell you, do you have a reaction that lies far to the right, where most of it is going to get converted to products, or do you have a reaction that lies far to the left, where hardly any of those are going to get converted to products? The way that we write that is we take the concentration of each product and we raise it to the power of whatever the coefficient is. So if I look at this general equation right here, I can see that my K value for the reaction would be equal to the concentration of C raised to this power. So whatever number I have here, that's the power I raise this to. And we do that for each reactant. And then on the bottom is going to be, my reactants on the bottom, my products on top. Sometimes you'll see a little symbol at the bottom here, so it could be C or P. Kc just means that you're dealing with aqueous solutions or concentrations in moles per liter. If you see Kp, that means you're dealing with pressures or partial pressures where only gases are included. But it's going to be set up the same way where you've got products over the reactants. The C or the P is just indicating if it's concentrations or pressures. So let's learn how to write those with a couple examples. One key thing right here is that only gases and then aqueous solutions are going to be included in these equilibrium expressions. So when you have to write an equilibrium expression, you are not going to include solids or liquids. So no pure solids or pure liquids, only if it's an aqueous solution that has a concentration or gases. So let's take a look at this first one right here. We've got N2 gas plus H2 gas, and then we've got ammonia over here, NH3 gas. If we're going to write the equilibrium expression for this, now I notice that they're all gases, and so for this, to write my equilibrium expression, that's going to be in terms of the partial pressures. So really we could write Kp. And again, we're going to have our products on top. So my only product is NH3. The way I'm going to write this is instead of putting it in brackets, we're going to write a capital P, and then we're going to go NH3, saying the partial pressure of NH3, or the pressure of NH3 gas is what we mean. And then we're going to raise it to the power of whatever coefficient I've got, which is 2 in this case. So it's going to be the pressure of NH3 squared on top over my reactants. So I've got the pressure of H2. That's going to be cubed or raised to the third power, and then times the pressure of N2 gas. And there's a 1 here, so we're just going to leave that. We don't have to label a 1 there. We're just going to leave it blank. And that would be my equilibrium expression then for this reaction. For this one right here, again, I see a couple things here. First of all, I've got solid KClO3. Solids are not going to be included in my expression here. And this is not going to be included either because it's also a solid. So I'm only going to have one thing in my equilibrium expression. It's going to be oxygen gas. And again, it's a gas, so I'm going to write Kp. Now, it's going to be products over reactants, but none of my reactants are going to be in this equation. And so really all I'm going to have is the pressure of O2 to the third power. And that right there would be my equilibrium expression for this one. For this last one here, we've got NH3 aqueous, I've got liquid water, NH4 plus aqueous, and then OH minus aqueous. So I'm including these two and then the NH3, but not the H2O because it's a pure liquid, and pure liquids and solids are not going to be in my equilibrium expression. Also, these are aqueous solutions, so instead of pressure, it's going to be concentration. So Kc. On the top, I'm going to have the concentration of NH4 plus. I've got nothing in front here, so again, I'm not going to put a 1 or anything, just leave it like that, times the concentration of OH minus over concentration of NH3. And that would be my equilibrium expression then for this reaction.